next example. And here I am looking at this example that has an evenly distributed force on pretty much what the simply supported beam is. So from here to here, I have a simply supported beam. And then on the right side, I have a cantilever, and the cantilever and the simply supported beam are shared by the hinge in the middle, and the hinge effectively, or like the cantilever, provides the simply supported beam support, but all in one system here. So let's make some observations here before we get started, because we don't want to really calculate it, we just want to understand the system. So first of all, here's the hinge at x equals to 4 meters. I know that my moment must go through 0 there. What else do I know? I know that my shear force in this first domain, let's call this here the first domain. So the first domain, actually let's call it domain 1, domain 2, and domain 3. And in the first domain, let's say the shear force here, V must be linear, constant, and constant. That is no different than before. My moment would be quadratic, so x squared. This here would be linear, or x, and this would be also x. So now it's just a matter of solving the problem, and we learned already before that we can break this down into the two subsystems, the cantilever on the right side, the simply supported beam on the left side, and therefore all we have to do now is find the support reaction and use this to solve our problem. I'm going to make my life very easy here because I have a cantilever on the right side. All I need to do really is find what's called RAY here, RAY on the left side, and once I have that, I can just work my way from left to right. So let's find RAY first. Actually, that's very simple in this case. RAY is really only dependent on what goes on in this subsystem here. So in that subsystem, I really have only 40 times 4 divided by 2, if I will. And that is, this can be a little bit deceiving because it seems like everything here on the right has no influence on that, but that is not really true. It just works out that way because of the hinge. And so the hinge really allows me to look at this as my RAY has to put the 40, everything here has to put in balance, right? So RAY puts that in balance. So let's look at that. So I have 40 times 4 divided by 2 effectively, right? So that would be 80. So now that I know that my support reaction there is 80, I guess one other thing I should do quickly is calculate my x and y components of this force because it will make my life easier. So let's do that. And that is nothing else than 200 times cosine 75. And this here would be 200 times sine 75. All right, so now I can go ahead and use that information to deal with my system here. And what I like to do when I draw these internal force diagrams is to bring all my important domains down, if you will, like so, share them with the system so that I have all diagrams in line with each other. All right, so on the left side, I have a roller. Now we're talking about a normal force diagram, normal force, and normal force here happens to be in kilonewton. And on the left side, I have a roller. That means the normal force cannot be resisted or created, so everything here has to be equal to 0. So I'm going to indicate that by a line through there. In that second domain, this very same thing is true. But in the last domain, I have to be careful now. I have to differentiate between tension and compression, and it's clearly in tension because the force is resisted at the support and it's created here by the 200 times cosine 75. So I am going to say that in tension. I'm not just saying that, it's correct. So tension is positive and it's constant from there to there. So this is my tensile component and it's constant. And the value here really is RBX, which is also equal to 200 times cosine 75. And we're already done with that, except that I probably should put a result there, which is 51.76. 51.76. All right, now I can move on to my shear force diagram. So let's do that. First, always I indicate what units I have and which diagram I'm dealing with. And in this case, it's fairly straightforward. I'm following my arrows. Since I'm starting on the left side, I am going up by 80, plus 80, and then it's linear down, right? So it goes linear down, and since it's an evenly distributed force that slopes down with 40 kilonewton per meter over 4 meter, it has to go down here to negative 80, if you will, right? And now it has to stay constant because there's nothing that happens between those 2 points. So I'm gonna go this way. And then it has to go down by the addition of 200 times sine 75. So I'm doing that. And then it stays constant. And then I reach my maximum. And this then should be RBY. And RBY in this case happens to be 273.2. So 273.2. And last but not least, I have to indicate my areas here. And it's important to note for somebody who has never dealt with these hinges before in the diagrams that there is a shear force value here at the hinge. It's a very common mistake that students start to believe everything there must be equal to 0, but that's not true. Only the moment goes through 0. And in fact, let's get started on that. We're going to start with the moment diagram in kilonewton meters. And I know that I have to go through 0 here. I know that I have to go through 0 here. And I know that nowhere else is really 0, except like when it passes through 0, that can happen sometimes. But another thing that I know that's very helpful to solve this problem is that there's a maximum exactly where the shear force is going through 0. And that, of course, happens at x equals to 2 meters, right? This is fairly obvious in this problem. So x equals to 2 meters. And now I also know that my system must be parabolic there, so it must be x squared. And so I just pretend I can draw a perfect parabola. And it has to start from the left to the right with the positive slope that gets less and less and less. So I know that from this part here. Right, so I know that here I have a positive slope that's very high, so I have a slope of 80, so this is very steep slope here, and then here, let's say in the middle it's 40, so now my slope goes down, and then I will go to a slope of 0, so here the tangent to that line would be 0. So once again, I can use the very same logic that I used before. And of course, my hand drawing is not perfect, but it gets the point across. And so now you see that at this location here, pretty much at the continuation from the linear slope to the constant, they have the same value. What that means is that here in the moment diagram on the left side, the tangent is identical to the tangent on the right side here. And so I can therefore, not that my hand drawing can really show this, but what I can do now is I can continue that tangent which goes down, and so ideally that matches my parabola there. And now I see that my slope gets steeper at this point because we have a drop from here to here. So at that so from x equals to 5 meters to x equals to 5.1 meter, if you will, we must have a steeper slope. So I'm going to have a steeper slope there. I pretend that I can draw that easily. So I'm going to zoom out. So there must be a kink in the moment diagram. And now I can close my diagram. And I know that this is negative, this is positive. The last thing I now would have to do is calculate the moment. And the moment at this location here is m min, if you will. I also have to calculate the moment here, which is m max. And how do I calculate the moment? Always the same way as I learned in previous lectures, and that is I just make my cut there. Sometimes I can do it in my head, or I can do it, just like drawing it out myself. But for the first portion, I'm gonna show this here on the top. I'm gonna cut exactly through that point. And so my m max would be equal to the support reaction, RAY, times 2 meters. And now minus, right? Minus 40 times 2 times 2 halves, which is 1. And so that would give me my R max, which also happens to be like WL square over 8 in this case, because it is a simply supported beam, but this happens to be 80, right? So, and this is positive 80. For the M min, it becomes a little bit more complicated because it's probably the easiest to start from the left side and cut the entire system. So what would I do? I would say, if I want to be like really diligent, I would say the sum of the forces, the sum of the moments is equal to 0. And I'll turn counterclockwise positive, and 0 is equal to, so negative RAY times 6 meters plus 40 kilonewton per meter multiplied by 4 meters multiplied by, now I need to be careful, 4 over 2 plus 1 plus 1 meters. And then also plus 200 kilonewton times cosine, sorry, no, that's not right, sine 75 multiplied by 1 meter, that's the lever arm. And then plus the moment, right? Plus m min, plus minus m min, depends on which direction you rotate it. And when you do that, you will find that m min is really the support reaction at that location, which happens to be 353.2. So therefore m min is equal to minus 353.2 kilonewton meter. And this is how I solve these internal force diagrams with minimal calculations, and also with paying attention to the moment diagram. Sorry, the hinge and the moment diagram as it relates to the hinge. And I say it again, the hinge means that the moment goes through 0, but not anything else. It's just coincident that in the moment in the normal force diagram, that it passes through 0, 2. That is due to the forces, to the force system and how the forces are applied to the system. That has nothing to do with the hinge. If there was a force that acts horizontally on the system to the left side of the hinge, there would be a normal force that passes through that hinge as well. So only in the moment diagram that goes to 0. And the calculation of any value didn't change at all. So all of that stays the same. So here's the whole system again. And that is how you can calculate your diagrams. So now we have a system that's very similar, except now we do not have a cantilever. We actually have a simply supported beam on the left with an overhang and then a support on the right side. And we need to be careful here because we also have a concentrated moment. And so that we need to pay attention to. So what do I know? I guess I can even without calculation start a few things, and that's my goal in this problem, to just show you like where you can already find your first clues. So let's again draw the normal force diagram, which in this case is in kilonewton. And then we do the shear force diagram, which is also in kilonewton. And then we do the moment diagram in kilonewton meter. So let's start. I know already that my moment must pass through 0 here, through 0 here, through 0 here. Already got that figured out. I already know that the normal force is effectively 0 everywhere. I don't have to worry about that. There's no horizontal force. So let's get that over with. I also know that my shear force diagram, and we think of this in domains again, right? So let's call this here D1, D2, D3, and D4. And in D1 and D2, my shear force diagram must be linear, then constant, and then constant. And now very careful, because for the moment diagram, I cannot just integrate in this case because of the concentrated moment. That concentrated moment means that here in my moment diagram, I will have a jump. Just like a concentrated force causes a jump in the shear force diagram, a concentrated moment causes a jump in the moment diagram. So I know that I have a jump there. But I also know that I will have x squared here and x squared here, and then x and x. Yeah, and then I think we should start with calculating our support reactions and move on from there. Because once we have the support reaction, everything else becomes easy. In this case, I would start with the support reaction on the far right. That's what I'm going to do. Why am I doing this? Because I just have to worry about this system here on the right side. So all I have to do is make sure that RCY balances the 200 kilonewton meter. So the equation would be 0 is equal to plus RCY times 2 meters plus, no, sorry, that's not true, minus 200 kilonewton meter must be equal to 0. So effectively, RCY is equal to 200 kilonewton meter divided by 2 meter. And that effectively gives us 100 kilonewton. So now I know that, 100 kilonewton. And that, of course, is going upwards in this case, right? So I already made that balance. So I already assumed here that is going upwards, and I can tell from experience that is turning counterclockwise, and the concentrated moment is turning clockwise. So therefore they can balance each other. So therefore it's a positive result here, and that means it's pointing up. So that's good. Now I can continue that and calculate my other support reaction. That's not the point of today's lecture. So, but I can just tell you, you could just find this support reaction, which I call RBY, by taking the sum of the moments about the support at A. And when you do that, you will find that actually RBY must be negative. So it must go down. And therefore I'm going to erase this arrowhead here and rotate it around. So RBY actually happens to be 40 kilonewton, but downwards. And then you can find the last support reaction very easily. No matter how you want to do it, you can do it by the sum of the moments about any point, or you can do it by the sum of the forces. For a beginner, I would not recommend the sum of the forces being equal to 0, because that should be left as a check. But I can be okay with that here because I already checked my work. And again, this is just for, showing the internal force diagram. So we're not worried about support reactions here. So RAY comes out to be 100 kilonewton. And now I can easily draw my diagrams just like I'm used to it. In fact, let's use our favorite method of starting on the left side. For the shear force diagram, I'm going to go up with 100. And then I have to go down with 40 per meter over 2 meters. So 100 minus 80 effectively is where I'm ending up. So that means that here I am at 20, whereas here I am at 100. And then I have a jump of 40 down, because I'm still following my arrows. And you can, of course, always make a cut and calculate and convince yourself. But now I have minus 20. And my slope has to continue because the slope of negative 40 did not change. So I'm going down with negative 40 for each meter. And so I'm ending up at effectively minus 100, which is a good thing, because now it has to stay constant, right? Nothing has to change. Even though there's a moment, nothing changes. There's a concentrated moment at x equals to 5 meters, but it cannot change. And this also allows me to use RCY to bring it back to 0, which is really our goal here. So we already completed the shear force diagram. And once again, you see that the shear force diagram is not going through 0, although there's a hinge there, right? So that will be different for the moment diagram, of course, now, but we'll focus on that in a second. For now, what you saw is that the shear force diagram can be treated just like any other shear force diagram, although we have a hinge in there. And the system really doesn't behave any differently, except that the moment must be 0 there. So let's take a look at our moment diagram. So now I know a little bit more about it. I know that I must have a maximum or minimum at the location where the shear force goes through 0, and that would be here at this location at x equals to 2 meters. So is it positive or negative? I have to be careful about that now, but I'm starting here at 100, so I have a high slope, and then my slope gets less and less, and then I pass through 0 instantaneously. So let us draw the slope upwards, 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 and then I have to have a slope of 0 there. Actually, it's funny, there's like an immediate kink there because it jumps to 0, the shear force diagram. But once again, you see here I have a higher value of slope and a positive slope. By the way, don't be fooled by this going down. it is all positive, positive, positive. So therefore, I need to have a positive slope, positive slope, positive slope, positive slope. And what that means is here I have a very steep slope of 100. Here I have less than 100 slope. And here I have a slope of like 20. And then it goes to 0. And now the same is true in reverse. Here it becomes a negative slope until I hit the 100. So if I want to continue that, I'm going to go down. And once again, I have to point to it again. Once again, here is the slope that ends at 100 and then it moves over to constant 100. That means that here on the left side, I have a slope of negative 100 and here on the right side as well. So the right side is a continuation of that very last piece of my parabola there. So let's draw that. And again, that's linear. So I'm going to try to use a ruler. And now I need to be very careful because yes, it goes down to that point. And yes, I have to end up at 0 here at x equals to 6 meters. But something has to happen in between because you can argue this two ways. Number one, you have this concentrated moment there. But also number two, we have still a negative slope. And if I want to, so I'm going to show that again with my pointer. So if I want to get from here to 0 with a negative slope, that does not work, right? So I have to jump up here and then go down. And so this line already proves that here I have to have a negative line and jump down. So let's do that jump. So my moment diagram actually looks something like this, which now is, by the way, easy to calculate because it's 100 times 1 meter. And so therefore I have, at this location here, I have a value of 100 times 1 meter, which of course is 100. And then I have to subtract the 200 from there. So this here is effectively minus 100. And then this is positive and this is negative. This is all positive. And then I effectively finished my diagram. And so you see, once again, the moment diagram is no different than before, except that your moment has to pass through 0, of course, where your hinge is situated, and nothing else goes through 0. In this problem, we also added this nice little feature of the concentrated moment to make us aware of the fact that the concentrated moment is kind of similar, that it has an effect on the moment diagram, but nothing on the shear force diagram. And I think this concludes the problem, and we solved it completely.